Hello everyone. My dissertation title is A Knowledge-Based Approach to Reducing Complexity of Maintaining Semantic Constraints in Data Exchange and Integration. Let's look at my outline first. First, I will describe the current business data validation challenge and give an overview for syntax and semantic validation. Second, I will list the limitation of current data validation technologies. Then, I will summarize my problem statement and solution methodology. In the part 4, I will introduce the design and implementation of a reusable software framework for integrated XML data, syntax, semantic validation. In the part 5, I will introduce the knowledge-based semantic constraints specification and validation. Then, I will list my expected contributions. Finally, I will show you my work plan and related reference. Okay, let's see business data validation challenges first. The Gartner report indicates poor data quality is a primary reason for 40% of all business initiatives failing to achieve their targeted benefits. The business influence of the staggering figure is evident to the enterprise, and doesn't matter how fast, how much, or how diverse the kind of data an enterprise collects. If the data is misaligned, missing key attributes, or is unreliable. Thus, saving business data integration and validation has become ever more important and challenging. Generally, business data are typically represented in XML and exchanged among their producer and consumers. For effective data communication and integration, the XML documents must be syntactically valid and semantically meaningful. So, the syntax and semantic validation are very important for XML documents. Let's look at the syntax validation first. The document type, definition, and XML schema are used to specify XML syntax. They define the syntax and the data types that all of its XML instance documents must confirm. XML data will be generated in accordance to their DTD or XSD definition. The simple API for XML and the document object model are the dominant paths for validating document syntax. They can be used to find out whether the XML instance document is well and correctly formed. Let's see an example. The mailing address is one important business data for product shipments between business and customers. A typical mailing address is like the one on the left. The main components include recipient name, optional recipient title, optional apartment number, street number, street name, city name, state name, zip code, and optional country name. In the middle of pictures, the XSD segment defines that the root element must be the mailing address, which includes recipient, street, region, country, and zip element, and one attribute, type. We can validate the XML instance against this SSD document by sex or DOM parser. This process can be called syntax validation. In addition to syntax validation, there is a need to perform semantic validation, because not all constraints can be defined using DTD or XSD. Semantic constraints are basically constraints on XML data or values. The existence of the value for an element or attribute. The correlation among the values of several elements and attributes. Schematron is the dominant industry standard language that uses XML parse language expression for specifying semantic constraints on business data. XParse is a W3C recommendation that uses path expression to navigate elements and attributes in an XML document. Schematron was initially proposed in 2001 by Academia Sinica Computing Center, and Schematron 1.5 and 1.6 were their most popular version until 2005. Since this year, ISO Schematron becomes an industry standard and introduces additional features. There are 4 layers in Schematron hierarchy: schema, pattern, rule, and assert. Each assertion is grouped into rules and defines a test attribute, and each rule defines a context attribute. Each rule is then grouped into patterns, and each pattern defines an ID attribute. Each pattern is grouped into the root element schema. This schematron document specifies 5 semantic constraints. Let's take the first semantic constraint as an example to explain the schematron validator how to work. The first one will check whether a city element is included in the address information. The specified path is mailing address, region, city, and a validator will check the location in the XML instance. If the validator could find it, the validator would pass the validation. If not, would return the error information. Currently, the industry normally uses the XSAL and SSLT to validate an XML document against the schematron document. In the following, I will list the limitations of the current data validation technologies. The first limitation is separate syntax semantic validation. This figure demonstrates that the XSLT-based semantic validation process, which involves 2 transformations. First, it transforms a schematron document into a validating style sheet in an XSLT engine. Then, it executes the validating style sheet in the XSLT engine to perform validation for the XML document to generate a final report. Clearly, syntax validation is not part of schematron validation. We have proved that such separated validation process may lead to invalid semantic validation result. Let's look at an example. The XSD document specifies that an address element has an attribute type whose default value could be shipping. The XML document contains one address element without the type attribute. The schematron segment specifies that the address element must have the type attribute with value shipping. The root element address may have an attribute type, but is not required. The information of XML instance actually includes the default value shipping for attribute type, while the default value is available during syntax validation, but is not available in such semantic validation implementation. The second limitation is that semantic validation is not reusable software component supporting runtime decision-making. XML validation is an important process frequently used in many applications, and is inefficient to implement repeatedly. XSL, XSLT-based semantic validation result is for people to review. The XSLT-based validator would print out the validation results that are only for the valid information. It's difficult for users to make a decision based on the current validation results. Meanwhile, we also found that different companies may adopt different XML syntax to represent similar business data. On the other hand, for the same XML dialect, its different versions may differ in syntax. We need to maintain a large growing pool of different versions of semantic constraints, which can easily lead to chaos and consistency errors. It greatly increases the complexity and reduces the work efficiency. These three mailing address XML documents are representing the same meaning, but the structure and business metadata have changed. We must create new schematron documents for each instance. It's reasonable to assume we will need n number of schematron documents for n number of XML syntax. Without a doubt, we cannot use a brute force approach to validate them. The number of schematron documents would grow linearly as the syntax variations grow. My research aims at improving the correctness and efficiency of binary data syntax semantic validation, reducing the complexity in maintaining the ever-growing semantic constraints based on the diverse syntax of binary data, and supporting knowledge-driven decision-making and data integration. Our reusable software framework will be designed and implemented to validate the approach. The following is solution methodology. The first one is integrating XML syntax and semantic validation process for avoid the invalid the validation results. The second one is generalizing all support from ontology to knowledge graph for supporting customer relation as a first-class relation in all documents. The third one is specifying semantic constraints at the knowledge graph level. It ensures we only need to maintain one schematron document. The next one is automatic mapping of conceptual level semantic constraints to schematron constraints. It ensures we could make normal semantic validation for each instance. The last one is a reusable software framework for flexible data-driven decision-making. Okay, let's solve the correctness problem first. This research designs and implements a reusable software component to integrate syntax and semantic validation for XML documents. Furthermore, this component supports all of schematron ISO features and data-driven decision-making. This problem can be divided into four subproblems. The first one is integrating syntax and semantic validation. This picture shows our design. The DOM parser is first used to validate the XML document against its Excel schema documents, and all information in the XML and XSD documents is represented and stored in the resulting DOM tree to the left. The same DOM parser also can be used to validate the syntax of schematron documents against its XSD documents. The resulting DOM tree to the right represents the schematron document. Both of the two DOM trees are fed to our new XPath-based schematron validator for semantic validation and obtain the final validation result. This process combines syntax validation with semantic validation and takes the derived information from syntax validation for reusing in the semantic validation by DOM parser, therefore saving default values in the syntax validation, which may alert the result of the semantic validation. The second subproblem is developing a reusable software component. This software component is developed as an API, can run as command line. We select Java programming language to develop this component, can accept the XML schema file, XML file, and schematron file to perform the validations required. The third subproblem is supporting all of ISO's schematron features. Compared with the previous schematron versions, there are some changes and extensions in the ISO schematron. Our research created a middleware parser supports these new features. More specifically, they are supporting phase for selective validation of different project stages. The second one is supporting abstract pattern rules for semantic constraints reuse. The third one is supporting let for variables in schematron document. Next, supporting include for semantic constraint reuse. The last one is supporting key function for evaluating the target value. The last sub-problem is supporting runtime decision-making. Our research can help the user to understand the whole validation process clearly, and also discuss how the validation result can be used to integrate with the external APIs to deliver the information needed to make decisions. In the following, we need to solve the efficiency problem. We propose a knowledge-based approach by extending out to support the effective concept-level representation of semantic constraints on business data. We only need to design and maintain one schematron document for similar business data constraints, thus reduce complexity. The research also supports the customer function to extend the capability of XPath in the integrated syntax and semantic validator. This problem also can be divided into 4 subproblems. I will introduce them one by one later. Facing our problem, we notice that the compared concepts never changed, which means they are describing the same meaning and effect. If we can express that specified concept in a formalized manner, we can create the semantic validation rules based on the concept instead of structure. With the same the concept, we can think of the ontology can define and express concept, and attempt to use a knowledge-based approach to solve this challenge. Ontology is one of popular model for knowledge representation of a particular domain of discourse, which defines concept and the relations between objects. But there are some limitations in current ontology. The web ontology language is dominant industry standard for representing relations among entities to encode domain knowledge as ontology. The all document relates two classes together using the is-a relation, which is currently the only first-class relation used between classes. For example, in the left figure, there are 5 entities. Eye is an organ, heart is an organ, but we cannot describe the relation between body and heart, although we all know they are whole-part relationship. In the current industry, there are some tools make it easier to build ontologies, such as Stanford University Portagy. If users would like to represent relations in Portagy, they can use object property to create a relationship between two individuals. But object properties must have a domain and a range specified. It will link an individual from the domain to another individual from the range. We still use our address XML instance as an example. The object property part of 1 would link country to state. In this case, the domain is mailing address, and the range is region. The object property part of 2 will link city to zip. The domain is region, and the range is mailing address. We found that the object property part of 1 and part of 2 are not first class relationships, which means they cannot be used by all to relate random to classes like is-a relationship, because the kind of relationships is only applied in a certain range, and they cannot be placed each other. So if the user would like to create the kind of part-of relationships, which will be generated many times by different name. According to our address example, an idle-all document is shown in like the picture. Each address instance should be a special case of address concept. Other concepts should be a part of address instance, but we cannot create by cardinal. Pace University extend all with minimum syntax extension to allow domain experts to declare customer relations with various mathematical properties. The resulting knowledge representation is called knowledge graph. Pace University also extend Stanford University's project for Pace Protege to allow domain experts to visually declare customer relations and encode knowledge. In the right figure, customer relation part of can be used in any two classes without the requirement of range and domain. The customer relation of Pace Protege can be used as the first class in any level. The first subproblem is specifying abstract semantic constraints for reducing constraints management complexity. According to our previous analysis, an abstract schematron document could be created at a conceptual level, replacing the original XPath expression with placeholder $sign and concept names, and the corresponding abstract concepts based on the knowledge graph. These 8 concepts need to be processed. In the same domain, there are lots of different dialect data to describe the same meaning. It's possible that they have some common elements, attributes, or similar structure. The greater possibility is that they have different element, attribute names, and structures, and even seemingly unrelated data are expressing the same meaning. They could share one abstract schematron document if the same semantic constraints are used. The second subproblem is automatic conversion of abstract semantic constraints to concrete ones. This process includes 2 steps: generate a mapping table and mapping the abstract semantic constraints to concrete one. The mapping table is typically a simple text file containing name-value pairs separated by an equal sign. The name to the left of equal sign is the value of all class RDF about, which represents the name of an abstract concept. The value on the right side is the XPath expression of the given XML instance document. For different XML instance documents, we need to generate a mapping table for them. According to the mapping table, there are 8 pairs of name-value entries. For example, the abstract concept city is used in the abstract schematron document for 3 times. When the validator with the entry all $city would be replaced with region city. After data exchange, we could get the concrete schematron documents for each instance. The third subproblem is extension of previous framework for supporting abstract semantic constraints. The current knowledge-based validator is an extension of the previous integrated validator. Since IT staff and domain experts are typically involved in the integration activities, it's natural to engage them. IT staff can collaborate with a domain expert to accomplish it. The overall design of the conceptual level validator is shown in this picture. Domain experts can use the PACE topology to create a knowledge graph, and an abstract schematron document can be generated. Data publisher needs to read the knowledge graph and understand which concepts are available. Then, data publisher defines a mapping table according to the given business data. Through data exchange, the validator could generate the concrete schematron document for each instance. Finally, we could use the concrete schematron documents to finish the semantic validation. The last sub-problem is supporting customer function in XPath expression. The use of XPath is also very important and necessary in our research. Because our validator is based on XPath, customer XPath functions are user-defined XPath function, can be called from any XPath expression within the Xforms document. Our purpose is that users can use these XPath functions in the same way that using any built-in XPath function within an expression. As stated in previous slides, the simple schematron document has two semantic co-constraints, which cannot be handled by any built-in XPath function. The hash sign is added before each customer function, which can help us to retrieve the appearance of them. Our research proposed one solution to solve this problem by reflection mechanism. Our expected contributions are: specify semantic constraints with more generic concepts instead of XML type attribute names. The second one is provide automatic mapping method from conceptual level semantic constraints to schematron constraints. The third one is provide a reusable software framework for integrated XML syntax and semantic validation. The first one is reduce complexity by introducing an ontology and going further by using a knowledge graph to support more economical specifications of schematron documents for XML semantic constraints validation. The last one is reduction of complexity of maintaining multiple versions of such semantic validation rules by unique use of knowledge graph. After proposal, I will optimize design and implementation of conceptual semantic constraints specification validation, and finish the experimental validation with HL7-based medical applications. Thank you.